previous 2 or 3 lectures, what we have learned is that the dynamics of a rigid body is governed by the change in its angular momentum by the externally applied force. However, we dealt with simple problems where the axis of rotation was fixed in space and the body was rotating about it. In this case, the entire relationship became very simple and we showed that L equals I omega, where I is the moment of inertia and omega is the angular speed. In the fixed axis rotation, where the axis was either fixed in space or it could move parallel to itself, all we could do in rotations was change the magnitude of omega and therefore change the magnitude of L. We also applied the principle of conservation of angular momentum, where we in one demonstration changed the value of I by pulling my hands in and out. All we did in these problems was only change the momentum, the magnitude of angular momentum and angular velocity. However, when we started, we wrote L as a vector quantity which is equal to, for a given distribution of masses, mi Ri cross Vi. So, in principle, if there is a vector L, I should also be able to cause a change in it, not just by changing its magnitude, but changing its direction. So that if this was L1 and this was L1 plus delta L, this could be the change delta L in its magnitude. In that case, the axis of rotation may also change, and these kind of changes in delta L give rise to a little more complicated dynamics. The body may change orientation in many different ways. This I show by a few demonstrations after this. In this demonstration, I have these 4 cylinders. Let me show these shapes clearly to you. One is plain cylinder, the other one is cut like this, the third one is like this, and the fourth one is shaped, curved like this. The question we ask now is, which of these cylinders is going to go along this curved path when rolling from this side to that side? And let us see what happens. Let us first take this plain cylinder and roll it, and you see it goes straight but falls out of the tracks after some time. Let us look at this cylinder and let this roll, and let us see what it does. It rolls and you see it curves around the curves properly. Let us do it once more. You see this one goes through clearly. How about this cylinder? This goes over to one side, and how about this cylinder? This also falls over to one side. In this demonstration, I have this bicycle wheel which can spin on its axis. Let us see what happens when I put this end here. I pivot it here, it falls down. If I leave it, it will fall down. Let us see what happens if I give it a spin. If I give it a spin and leave it here, and you see it rotates. If I give it this spin the other way, you see it will rotate the other way. So what we observe is that when a rotation is given, instead of falling down, this starts going around like this, and this is known as precession. If I make it go faster, it goes around slower. If I let it go slow, then it goes around very fast. Slower it gets, faster it goes. So these are the things that we should be able to explain using rigid body dynamics. In this demonstration, what I want to show you is, if this wheel is not rotating, I can lift it up like this. You see, when I apply a torque like this, it goes like this. Now let me spin it and try to take it up. You see, it doesn't go up, it is going sideways. If I push it down, it goes sideways this way. Whereas when it is not spinning, I can take up and down by applying a torque like this. The moment I give it a spin, I give a torque up, it goes that way. I give a torque down, it goes this way. This is again a manifestation of rigid body dynamics and how torques and angular momentum interplay makes the dynamics very interesting. Here I have a device known as the gyro compass. In this, there are two frames that can rotate about two perpendicular axes independently. This frame can rotate like this about this axis. This frame can rotate like this about this axis, and there is a spinning wheel which can rotate about axes perpendicular to both of these like this. So in a way, x axis, y axis and z axis, there are three independent axes about which rotation can take place. Now I'll give the inner wheel a spin, and you see what happens when I rotate this. If I rotate this, you see the spinning wheel aligns with this rotation. Let me show it to you again. I give the inner wheel a spin. When I rotate this, the moment I rotate the outer frame, the spinning wheel, the spin axis aligns with the outer frame rotation axis. See it again. I give it a spin, rotate it. The moment I rotate it, it aligns with this. This can be used as a compass. Another interesting aspect in rigid body dynamics is, I have a box of sweets here with three sides unequal. Observe, when I give it a rotation like this and let it drop, it drops. Observe it carefully, it drops pretty much rotating about the same axis. On the other hand, if I give it a rotation about this axis, it again rotates in a very stable manner and drops. Observe now, when I do it about this axis, what happens? By the time it comes down, it has started rotating about all axes. Observe it carefully. It has started tumbling. We should be able to explain this using rigid body dynamics equations of motion. Whatever I have shown in these demonstrations can be easily explained by using the equation that rate of change of angular momentum is tau external. Not only that, you see, I was also, while doing these demonstrations, showing you how angular speed or angular velocity of the body was changing. So after having solved this equation, I should also be able to tell you how omega of a rigid body changes, and therefore with time how the body changes its orientation. To develop the theory of this, we need to be very, very specific about what does omega represent. Is it a vector? Is it a scalar? How about the orientation being described by vector theta? Can we do that? And how are L and omega related, so that once I calculate how L is changing, I could relate it to change in omega, and from omega I can find how the angle of a body with respect to different axes is changing. These are questions for which the answers come when we develop relationship between L and omega. We see how when L changes, how omega changes. We see how theta is related to omega, and so on. So we do that now.